Hi, welcome back to Easy Maths with Dr. Nasir, your path to math confidence. Don't forget to share, like, and subscribe so you never miss a conceptual concrete lesson. Well, in today's lecture, we will see some initial value problems while seeing an exercise. Find solution of the initial value problem dt by dt is equal to k into t minus tm where t belongs to r, t at 0 is equal to t naught, where k, tm, and t naught are constants. Also state the interval I subset of R over which the solution is defined. Well, see solution. The ODE 1.1 can be expressed as dt by dt minus kt is equal to minus ktm where t belongs to R. Comparing the ODE 1.2 with standard form, we have p of t is equal to minus k for t belongs to R. So integrating factor is mu of t is equal to exponential of integral of p of t dt, which is equal to exponential of integral of minus k dt. So mu of t is equal to exponential of minus kt where t belongs to r. Multiplying equation 1.2 by integrating factor, we have exponential of minus kt dt by dt minus k exponential of minus kt into t is equal to minus ktm into exponential of minus kt where t belongs to r. Well, this can be expressed as t by dt of exponential of minus kt into t is equal to minus ktm exponential of minus kt where t belongs to r. So we have d of exponential of minus kt into t is equal to minus ktm exponential of minus kt dt where t belongs to r. Now integrating, we have integral of d of exponential of minus kt into t is equal to minus ktm integral of exponential of minus kt dt plus c, where t belongs to r and c is arbitrary constant. So we have exponential of minus kt into t is equal to tm exponential of minus kt plus c, where t belongs to r and c is arbitrary constant. So t of t is equal to tm plus c exponential of kt, where t belongs to r and c is arbitrary constant, which is general solution of the ODE 1.1. Now using the initial condition 1.1, that is t at 0 is equal to t naught, we have t naught is equal to tm plus c exponential of k into 0. So t naught is equal to tm plus c. So c is equal to t naught minus tm. Therefore t of t is equal to tm plus t naught minus tm into exponential of kt where t belongs to r, which is solution of the initial value problem 1.1 and is defined over I is equal to r. Let's see another exercise. Find solution of the initial value problem x plus 1 into dy by dx plus y is equal to log x, where x belongs to 0 to plus infinity open interval, and the initial condition is y at 1 is equal to 10. Also state the interval I subset of r over which the solution is defined. Well, see solution. The ODE 1.4 can be expressed as dy by dx plus y over x plus 1 is equal to log of x over x plus 1, where x belongs to 0 to plus infinity open interval. Comparing the ODE 1.5 with standard form, we have p of x is equal to 1 over x plus 1, where x belongs to 0 to plus infinity open interval. So integrating factor is mu of x is equal to exponential of integral of p of x dx, which is equal to exponential of integral of 1 over x plus 1 dx, which is equal to exponential log of x plus 1 absolute, which is equal to x plus 1 absolute. So mu of x is equal to x plus 1, where x belongs to 0 to plus infinity open interval. Multiply equation 1.5 by integrating factor, we have x plus 1 into dy by dx plus y is equal to log x, where x belongs to 0 to plus infinity open interval. Well, this can be expressed as d by dx of x plus 1 into y is equal to log x, where x belongs to 0 to plus infinity open interval. So d of x plus 1 into y is equal to log x dx, where x belongs to 0 to plus infinity open interval. Now taking integral, we have integral of d of x plus 1 into y is equal to integral of log x dx plus c, where x belongs to 0 to plus infinity open interval and c is the arbitrary constant. So x plus 1 into y is equal to integral of log x dx plus c, where x belongs to 0 to plus infinity open interval and c is the arbitrary constant. So x plus 1 into y is equal to log x into x minus integral of x into 1 over x dx plus c, where x belongs to 0 to plus infinity open interval and c is the arbitrary constant. So x plus 1 into y is equal to log of x into x minus integral dx plus c, where s belongs to 0 to plus infinity open interval and c is arbitrary constant. So x plus 1 into y is equal to x log s minus s plus c, where x belongs to 0 to plus infinity open interval and c is arbitrary constant. While dividing this by s plus 1, we have y of x is equal to x log s minus s plus c over s plus 1, where s belongs to 0 to plus infinity open interval and c is arbitrary constant, which is general solution of the ODE 1.4. Now using the initial condition 1.4, that is y at 1 is equal to 10, we have 10 is equal to 1 into log of 1 minus 1 plus c over 1 plus 1. So 10 is equal to 0 minus 1 plus c over 2. So c is equal to 21. Therefore y of x is equal to s log s minus s plus 21 over s plus 1, where x belongs to 0 to plus infinity open interval, which is solution of the initial value problem 1.4 and is defined over I is equal to 0 to plus infinity open interval. Let's see another exercise. Find solution of the initial value problem dy by dx plus tangent x into y is equal to cosine square x, where x belongs to omega which is equal to r other than 4k plus minus 1 into pi by 2 such that k belongs to z, and initial condition is y at 0 is equal to minus 1. Also state the interval I is subset of R over which the solution is defined. Let's see solution. Comparing the ODE 1.8 with standard form, we have mu of x is equal to tangent x where x belongs to omega. So integrating factor is mu of x is equal to exponential of integral of p of x dx, which is equal to exponential of integral of tangent x dx, which is equal to exponential of minus log of cosine x absolute, which is equal to cosine x absolute x1 and minus 1. So mu of x is equal to secant x absolute where x belongs to omega. Multiplying the ODE 1.8 by the integrating factor, we have secant x absolute into dy by dx plus secant x absolute into tangent x into y is equal to secant x absolute into cosine square x where x belongs to omega. Now for x belongs to omega plus, which is equal to union over k belongs to z of 4k minus 1 into pi by 2 up to 4k plus 1 into pi by 2 open interval, secant x absolute is equal to secant x. Therefore from equation 1.9 we have secant x into dy by dx plus secant x into tangent x into y is equal to secant x into cosine square x where x belongs to omega plus. So secant x into dy by dx plus secant x into tangent x into y is equal to cosine x where x belongs to omega plus. Well, this can be expressed as dy by dx of secant x into y is equal to cosine x where x belongs to omega plus. So d of secant x into y is equal to cosine x dx where x belongs to omega plus. Now taking integral, we have integral of d of secant x into y is equal to integral of cosine x dx plus c where x belongs to omega plus and c is arbitrary constant. So secant x into y is equal to sin x plus c where x belongs to omega plus and c is arbitrary constant. So y of x is equal to sin x into cosine x plus c into cosine x where x belongs to omega plus and c is arbitrary constant. Also for x belongs to omega minus, which is omega other than omega plus, secant x absolute is equal to minus secant x. Therefore from equation 1.9 we have minus secant x into dy by dx minus secant x into tangent x into y is equal to minus secant x into cosine square x where x belongs to omega minus. So we have secant x into dy by dx plus secant x into tangent x into y is equal to cosine x where x belongs to omega minus. Well, this can be expressed as d by dx of secant x into y is equal to cosine x where x belongs to omega minus. So d of secant x into y is equal to cosine x dx where x belongs to omega minus. Now taking integral, we have integral of d of secant x into y is equal to integral of cosine x dx plus c where x belongs to omega minus and c is arbitrary constant. So secant x into y is equal to sin x plus c where x belongs to omega minus and c is arbitrary constant. So y of x is equal to sin x into cosine x plus c into cosine x where x belongs to omega minus and c is arbitrary constant. Thus from equations 1.10 and 1.11 we have y of x is equal to sin x into cosine x minus c cosine x where x belongs to omega and c is arbitrary constant, which is general solution of the ODE 1.8. Now using the initial condition 1.8, that is y at 0 is equal to minus 1, we have minus 1 is equal to sin 0 into cosine 0 plus c cosine 0. So we have c is equal to minus 1. Therefore y of x is equal to sin x minus 1 into cosine x where x belongs to minus pi by 2 to pi by 2 open interval, which is solution of the initial value problem 1.8. and is defined over I is equal to minus pi by 2 to pi by 2 open interval. We'll see another exercise. Find solution of the initial value problem dy by dx plus 2y is equal to f of x, where x equal to 0 to plus infinity closed interval, and y at 0 is equal to 0, where f of x is equal to 1 for x equal to 0 to 3 closed interval, and f of x is equal to 0 for x equal to 3 to plus infinity open interval. Also state the interval I is subset of R over which the solution is defined, and draw the graph of the solution. We'll see solution. Comparing the ODE 1.12 with standard form, we have u of x is equal to where x equal to 0 to plus infinity closed interval. So integrating factor is mu of x is equal to exponential of integral of p of s dx, which is equal to exponential of integral of 2 dx, which is equal to exponential of 2x, where x equal to 0 to plus infinity closed interval. Multiplying the ODE 1.12 by the integrating factor, we have exponential 2x divided by dx plus 2 exponential of 2x into y is equal to exponential of 2x into f of x, where x equal to 0 to plus infinity closed interval. Well, this can be expressed as d by dx of exponential 2x into y is equal to exponential 2x into f of x, where x equal to 0 to plus infinity closed interval. So we have d of exponential 2x into y is equal to exponential 2x into f of x dx, where x equal to 0 to plus infinity closed interval. Now integrating this from 0 to x, we have integral from 0 to x of d of exponential 2t y is equal to integral from 0 to x of exponential 2t into f of t dt, with x equal to 0 to plus infinity closed interval. So we have exponential 2t into y from 0 to x is equal to integral from 0 to x exponential 2t into f of t dt, where x equal to 0 to plus infinity closed interval. So exponential 2x into y of x is equal to integral from 0 to x of exponential 2t f of t dt, where x equal to 0 to plus infinity closed interval. Now for x equal to 0 to 3 closed interval from equation 1.13, we have exponential 2x y of x is equal to integral from 0 to x of exponential 2t dt, where x equal to 0 to 3 closed interval. So we have exponential 2x into y of x is equal to exponential 2t over 2 from 0 to x, where x equal to 0 to 3 closed interval. So we have exponential 2x into y of x is equal to exponential 2x over 2 minus exponential 2 into 0 over 2, where x equal to 0 to 3 closed interval. So y of x is equal to 1 minus exponential of minus 2x over 2, where x equal to 0 to 3 closed interval. Also for x equal to 3 to plus infinity open interval from equation 1.13, we have exponential 2x into y of x is equal to integral from 0 to x of exponential 2t f of t dt, where x equal to 3 to plus infinity open interval. So exponential 2x into y of x is equal to integral from 0 to 3 of exponential 2t dt plus integral from 3 to x exponential 2t into 0 dt, where x equal to 3 to plus infinity open interval. So exponential 2x into y of x is equal to exponential 2t over 2 from 0 to 3 plus 0, where x equal to 3 to plus infinity open interval. So exponential 2x into y of x is equal to exponential 6 minus 1 over 2, where x belongs to 3 to plus infinity open interval. So y of x is equal to exponential 6 minus 1 into exponential minus 2x over 2, where x belongs to 3 to plus infinity open interval. Thus from equations 1.14 and 1.15, we have y of x is equal to 1 by 2 into 1 minus exponential minus 2x, where x belongs to 0 to 3 closed interval, and y of x is equal to 1 by 2 into exponential 6 minus 1 into exponential of minus 2x, where x belongs to 3 to plus infinity open interval, which is required solution of the initial value problem 1.12 and is defined over I is equal to 0 to plus infinity closed interval. Well, this is graph of the solution of the initial value problem. The solution is continuous from 0 to plus infinity closed interval. Also, solution is differentiable from 0 to plus infinity closed interval except at is equal to 3. Well, in the next lecture, we will see some more exercises related to first order linear initial value problems. Don't forget to share, like, and subscribe Easy Math with Dr. Nasir so you never miss a conceptual concrete lesson.
Mm-hmm.